Picturing data. By the time we get done with this, we'll hopefully have a good understanding as to how to construct a bar graph and the usefulness of a bar graph. Also pie charts or circle graphs. How to build a circle graph. And also frequency histograms and frequency polygons. Okay. And also a time series graph too. All right, bar graphs usually represent categorical or qualitative data, non-numeric data, as is often the case with pie or circle graphs too. A pie chart, sometimes referred to as a circle graph, is in the form of a circle that is divided into sections that are proportional to the frequencies corresponding to various categories. And the nice thing about a pie graph or a circle chart is that it can help us see the relationship between the parts versus the whole of whatever it is that's being represented by the data. Here's an example of building a pie chart. The marketing firm Deloitte Retail conducted a survey of grocery shoppers. The frequency distribution below represents the responses to the survey question, how often do you bring your own bags when grocery shopping? Draw a pie chart to represent the data. The response categories are always, never, frequently, or occasionally. And these are the tally counts or the frequency counts for each of these categories. And we would like to build a circle graph or a pie chart that represents this frequency distribution table here. Okay. Now, you want to get technical building a pie graph or a circle graph. We know that in one circle, there's 360 degrees, correct? If you go all the way around, that's 360 degrees of rotation. All right. And so what we're going to do is we are going to take the frequency of each category and divide it by the total number of data points in the data set, and then multiply that fraction by 360 degrees. That will indicate what degree size the slice of the pie or the circle belongs to that category as far as degree measure is concerned. For instance, the always class, out of the 100 people that were randomly surveyed, 10 say that they always bring their own bags to the grocery store. So 10 over 100 is 1/10 times 360 degrees, which would be 36 degrees. So the always category or piece of the pie, if you will have a size of 36 degrees. Those who never bring grocery bags to the grocery store is 39/100ths of 360 degrees, which is 140.4 degrees. That would be the degree measure of that slice of the pie. Frequently would be 68.4 degrees, and occasionally would be the frequency of occurrence, 32 divided by 100 times 360, 115.2 degrees. Now, how are we going to measure these degrees out here? Well, you could use a protractor. But when you do these problems on ALEX, they're already going to have the degrees laid out around the circle. And so that it will be very easy for you to see, how to measure out the degrees. But if you were to build one of these by hand, you probably would want to use a protractor. And a protractor is this little guy right here that has degree measures, okay? Called a protractor. But you're not going to be building these manually. You're going to be building these on ALEX just by using your cursor. And so the always category will be a circle that has a measure of what was always 36 degrees. And so therefore this angle here is going to be 36 degrees, this angle. 36 degrees. That represents the always category. The never category consumes 140.4 degrees. So never, this angle here is an obtuse angle that measures 140.4 degrees. Frequently, what was its measure? 68.4 degrees was frequently. This is 68.4 degrees. And then occasionally consumes 115.2 degrees. 115.2 degrees. So all these degree measures add up to 360 degrees. And so you can see that the frequency of each category is proportional to the size of the piece or the sector of the circle that is devoted for that particular category. So the greater the frequency, the larger the size. Okay. And they also turn these frequencies into relative frequencies by dividing by 100 and multiplying by 10%, multiplying by 100% rather. And so just by looking at this category or this circle graph, you can determine very quickly that the most frequent response is that most people never bring their own grocery bags to the grocery store. All right, a very small sector, 10%, always bring their own grocery bags to the shopping experience. And so circle graphs can show you in a glance what category is the most frequently occurring versus least frequently occurring. And the circle graphs are in color, and you can even make 3D circle graphs, et cetera, et cetera. Excel makes the spreadsheet application can help you make a circle graph very quickly. But like I said on Alex, you're going to have all the tools you need to build a circle graph to answer the question. So it's not going to be an issue. And you'll know how many degrees to make your size of your sector of your circle, because they'll have the degrees laid out on a circle. All right. All right, a bar graph is used to compare frequency amounts or relative frequency amounts by using vertical or horizontal bars. Most most bar graphs are vertical in nature. Not all of them. Some textbooks or newspapers or media outlets use the horizontal way of representing bar graphs. They usually represent categorical data or qualitative data, unlike frequency histograms, which we'll look at. Here's an example of a frequency distribution table that we will use to make a bar graph. Survey of 100 grocery shoppers, again, is being used. Suppose the frequency distribution below represents the responses to the survey question. Which grocery stores have you shopped at in the last month? Publix, Trader Joe's, Fairway, Aldi, or other. Okay. All right. Now, ladies and gentlemen, do these frequencies add up to 100, do you think? There were 100 grocery shoppers randomly surveyed.
No.
In fact, it looks like they add up to a number that's larger than 100, quite much larger than 100. Do you agree? Now, why is that? Well, because when asked, some of these grocery shoppers actually shopped at what? More than one of these stores. Do you agree? And so the response is double or triple or quadruple accounted for, or even more accounted for. All right. And so I have a question for you. Would this particular frequency distribution table, would it be something that we could use to build a circle graph from, or not?
No, I don't think so.
Not at all. Because what's going to happen here is your frequencies sum up to something larger than the data set size, which was 100. And so the sizes of your sectors of your circle are going to be large, very large, and they're not going to add up. The degree measures are not going to add up to 360 degrees. The degree measures are going to add up to something much larger than 360 degrees, in which case you're not going to be able to make a circle graph of this data set. So if there's more than one response from your subjects, you should not be making a circle graph. You should be making like a bar graph. Okay. All right. And to make a bar graph is pretty simple. You have a vertical axis. You always want to start your vertical axis off at 0 and then have an appropriate scale to encompass all the frequencies of your categories. Notice they space these check marks on the vertical axis by 10 units apart. The horizontal axis represents the grocery store that was visited. Notice they are just qualitative or categorical labels of names of stores. You don't see any numeric like class limits from a frequency distribution table or that we seen the other day where we have actually classes, okay, with numeric classes. You don't see that. That's why bar graphs normally are used for qualitative data or categorical labelings or categories. All right, so Publix, how many people visited the Publix store? Well, that would be 50 of the 100 people surveyed visited the Publix stores. So this bar goes as high as 50, okay? And Fairway was the least visited store by these respondents. And only 28 people said that they visited Fairway. And so you can see that with a bar graph, you can ascertain a lot of information very quickly. It looks like other stores were favored among these named stores here by these respondents here. Okay. So that's called a bar graph. We've all seen bar graphs, maybe in magazines or newspapers or maybe many other places. So it's not something that we, are totally foreign to. Okay. All right. So like I said, when you have the possibility of having more, if you have more respondents for your categories than you have in your data set. In other words, if a respondent can choose more than one category, you should not be using a circle graph to represent the data. You should be using like a bar graph. Okay. And this is a classic example where a circle graph would not work. All right. All right. When data are organized into grouped frequency distributions, the grouped aspect means that we usually have numeric class limits or class intervals. Two types of graphs are commonly used to represent them. Frequency histograms or relative frequency histograms, and a graph called a frequency or relative frequency polygon graph. Okay. All right, what's a frequency histogram? Now, a frequency histogram looks like a bar graph in the sense that it has vertical or horizontal bars, but the main difference is the labeling on the horizontal axis. With bar graphs, you have qualitative labelings or you have non-numeric labelings of categories. With frequency histograms, all right, the horizontal axis actually has numeric class intervals. That's the main difference, okay? So we seen a couple of days ago whereby we could build a frequency distribution table with class limits or class intervals. And then we have our frequency counts over to the right here. And now this data set represents the record high temperatures in every state. It would therefore seem reasonable, if not expected, for us to illustrate the data graphically. And notice these frequencies should sum up to what? If these are record high temperatures in every state. Well, how many states do we have in the union here? So what do these sum up to? How many states are there? How many stars are on the American flag?
50.
This better add up to 50 then. Let's see if it does. 8 plus 3 is 11. 11 plus 16 is 27. 27 plus 13 is 40. 40 plus 7 is 47. Plus 3 is 50. Yes. Okay. So it looks like this works here. Notice our classes range from 100 all the way to 134. What would be the width of each class? What's the width of each of these classes?
Four.
No, not 4. You take the difference between successive lower limits or the difference between successive upper limits. So what's the width here?
5.
5. The width is 5. Notice there's no overlap between these classes. We indicated the importance of that a couple of days ago. Each class must have equal width. That's equally important. And you got to make sure that all your data lies in at least one of your classes. It has to be somewhere. All right, so this looks like a correct frequency histogram or frequency distribution table. And from it, ladies and gentlemen, we're going to build the graph, which is called a frequency histogram. Right. So let's go take a look at, see what this frequency histogram looks like. Okay. The vertical axis, just like with the bar graph, has a numeric scale on it. It starts at 0, and these tick marks are spaced 3 units apart. You just have to make sure that your scale on the vertical axis is adequate to encompass the largest frequency of any class. Notice they labeled the vertical axis as the number of states. Horizontal axis represents the temperature, the record high temperature. Notice we have our classes laid out on the horizontal axis. All right. And notice how we run these classes here. So the first class goes from 100 to 105. They don't say 100 to 104 and then have a little gap and then say 105 to 109, then a gap and say 110 to 114. They just run 100 all the way up to 105 and then 105 all the way up to 110. Okay, that's all right. There's nothing wrong with that. All right. And the height of each of these bars is going to be, equal to the frequency of that particular class. For instance, there were 3 states that had record high temperatures of between 100 and 105 degrees. It looks like the most common record high temperature was 110 to 115, where it looks like if we did not have the raw data set, if you project this horizontally back to the vertical axis, it looks like you would strike maybe about 16 states maybe, and record high temperatures between 110 and 115. This is called a frequency histogram. And again, what's the difference between a frequency histogram and a bar graph? What's the difference? Anybody? What's the main difference?
The bar graph is separate and the other one is all connected.
Well, yeah, I mean, the bars here have gaps in between them, but more importantly, what's the difference between the x-axis, the horizontal axis, between these two? There's a huge difference between the horizontal axis. The bar graph does not have what on the horizontal axis?
Numbers. It's all just going by
Yeah. It
category.
doesn't have numbers, doesn't have class intervals, numeric class intervals. It's just, qualitative labels, categorical labels, all right? Whereas the frequency histogram actually has numeric class intervals. Right? That's the main difference between a histogram versus a bar graph. All right. Next picture or graph is called a frequency polygon. It's similar to a histogram, but the main difference is you don't see bars, no bars. What you see are little line segments connecting points. And these points are the midpoints of the classes. The midpoints of the classes are connected by little line segments. Okay, that's what a frequency polygon is all about. So what we would have to do here is we would have to find the midpoint of each class here. So you'd probably maybe have an extra column here in your table called the midpoint column. All right, midpoint. And how do you find the midpoint of a class? Well, it's pretty simple. All you do is you just add up the endpoints. So 100 plus 104. You're going to add these up, and then you're going to divide by 2. That gives you 204 divided by 2. And what's 204 divided by 2? $102. So the midpoint of the first class would be 102. What would be the midpoint of the second class? 105 plus 109 is going to afford us 114 divided by 2, which is going to be what? 107. That's the midpoint of the second class, etc., etc., etc. 112 would be the average of 110 and 114. That's the midpoint of the third class. Do we understand how to get the midpoints here?
Yes.
All right. So the midpoints, and they're showing you what I just talked about here. Okay. All right. So ladies and gentlemen, here is a frequency polygon. After you have you add on that extra column to your frequency distribution table, that midpoint of each class column. You can see on the horizontal axis, which represents record high temperatures, vertical axis, the number of states again. So let's see here. What was 102? 102 was the midpoint of the what? First class, correct? And the first class occurred with frequency of 3. So you can see for 102, they have a dot which projects horizontally back to the vertical axis at 3, because there were 3 states that had a record high temperature of a midpoint value of 102 degrees. The midpoint of the second class was 107, and how many states fell in the second class? What is that, 9? About 9 there. What was the second class? Oh, it was 8. Okay. All right. And 112 degrees was the midpoint of the third class. And how many states had fell into the third class of record high temperatures? There were 16. All right. So this point here projects back to the vertical axis at 16. Although, you know what? Let's see. 1, 2, 3. Let me see something here. That sure doesn't look like it. $112 is the midpoint of 110 and 114, but the frequency is 16, isn't it? This don't look like it projects back to 16. What does this look like it projects back to?
18.
About 18. At this point should be way down here, maybe. Do you agree? There's about 16. That point should be about down here. That looks like a little glitch here on their part. So they should have connected these points right here and then went down there like this. Okay. All right, but we get the idea of how this thing goes. It's called a frequency polygon. It's like a line graph, okay, where the points that are connected by the line segments are they're the midpoints of the class, midpoint values. So that's called a frequency polygon. All right. And you know, the neat thing about a frequency polygon versus a frequency histogram is you can ascertain the same information about your data set. it looks like the highest occurring or the most frequently occurring record high temperature was between about 110 and 115 degrees. Same thing here, about 112 degrees, which is between 110 and 115 degrees. So the relative shape remains about the same between a frequency polygon versus frequency histogram. Obviously, the histogram uses bars and a polygon doesn't use bars, but we can still determine the same information in a general sense from both graphs. Okay. All right. Now, here are two group frequency distributions that come from data gathered in two calculus classes recently. One is for percentage on the final exam, and the other is for the overall percentage of the course. And notice these weird classes they got going on here. 40 to 49.9, and then 50 to 59.9. How wide is the classes for this first frequency distribution?
10.
10, 50 minus 40, or 59.9 minus 49.9. These classes are 10 units wide. What would you suspect would be the case between the average, or let's say the final exam percentage versus the overall average in the course grade? You would suspect that if a student has an overall, high percentage in the course for a course grade, that their final exam grade would be, in tune with that, and they would also score well in the final exam, and vice versa. Let's see if that's the case here. So what we're going to do is we're going to compute the, it looks like the midpoint of each of these classes, because we're going to build a frequency polygon. And this is going to be a dual frequency polygon, one for the final exam percentage and another one for the overall percentage in the course. And the midpoints for the classes are 44.95, 54.95, 64.95, et cetera, et cetera. So how did they get that 44.95? How did they get to 44.95 as being the midpoint of the first class? How did they get that? For this first class, how did they get that midpoint? They took the lower endpoint and added it to the upper endpoint and then divided by 2. They literally found the average of the endpoints of this first class. Or they performed linear interpolation between 40 and 49.9. And that gives you 44 point what? What was the midpoint they cited? 44.95 is the midpoint of the first class. So that's how they found the midpoints of all these classes. They just divided the sum of the lower and upper endpoint by 2. Okay. And when they did that, they then built a frequency polygon graph. One for the final exam percent score and one for the overall percent score in the course. Notice the horizontal axis is the percentages, and the vertical axis is the number of students. You can see that in general, when the final exam score basically peaks out up here, you can see that the student in general is doing well and very well in the course. As you would think that would be the case, right? I mean, you're not going to expect a student that's failing this course, ladies and gentlemen, to score 100% on the final exam. I mean, that would defy logic. I'm not saying it's not possible, because it is possible. Maybe the student wasn't paying attention throughout the whole semester and finally got it together on the final exam. It's possible, but it's highly unlikely. Okay. So you can see the relationship between the percent score on the final exam versus how the student was doing in the class as a whole. Okay. That's called a dual frequency polygon graph. And the nice thing about this is we can use it for comparison purposes. All right, that can be used for comparison purposes. Now, I have a question for you, ladies and gentlemen. Could I have made a dual frequency histogram from these two data sets here? Do you think that would have worked? From these two frequency distribution data sets here, do you think I could have made a dual frequency histogram?
I think so.
Well,
It might look messy.
say that again. It might look what? What was that word you said?
Messy.
Yeah, it's going to look extremely messy. Because what's going to happen is you're going to have these classes all aligned with each other. Do you agree? For the two different percentages. And you might have a bar that goes this high for maybe the overall class performance, and a bar that only goes this high for the what? The final exam. And I mean, you'd have to come up with some sort of a coloring scheme to differentiate these two as to, you know, which one pertains to the final exam percent versus which one pertains to the overall course percentage. And if you come up with a color scheme to differentiate that, you know, I mean, it might be possible, but it seems like it might be a little bit messy here to determine which is which, you know what I'm saying? Which pertains to which percent. So it might be better that they've constructed a dual a frequency polygon graph for this situation, as opposed to a dual, you know, frequency histogram in this particular situation here. I'm not saying it's not possible, but like you said, it probably would be a little bit messier. And for that reason, yeah, you might want to just go with like something like this, right? Easier to compare and see the differences and similarities. All right. Now, a time series graph. A time series graph, as the name suggests, involves data that's collected where one of your coordinates of your ordered pair, ladies and gentlemen, represents time, whether that be in days or weeks or months or years. Time has to be one of your axes for a time series plot or a time series graph. Okay. The nice thing about a time series plot or graph is that it can show you very quickly any trends or that exist in your data. And where would a time series graph be very useful out there in the real world, in the business world, ladies and gentlemen? Can anybody think of a classic example where a time series plot would be very useful in, let's say, the business sector out there? In fact, they're used every single day, whether they're on a computer screen.
Time plot.
Yeah, time plot. Can you think of an area in the business sector where the time plot is very useful?
Projections of sales.
Sales, that would be, yeah, one area, one good example. Any other examples where time series plots are very useful? Yeah, projecting, you know, sales versus time. How about the what do we got on Wall Street in New York? What hangs out on Wall Street? It's called the
Stock exchange.
Stock exchange. Do you agree? Stocks. Yeah, stocks are always changing with time. Stock prices. It's a very volatile market, the stock exchange. Yeah, you bet. And there's a lot of stock analysts that use time series plots to try to model trends that exist in the time series plots so as to make educated guesses as to what's going to happen in the future for stocks, so that they can, you know, inform their clients or their customers, you know, what to do with their money. Okay, whether they should pull it out of the stock or invest more, et cetera, et cetera. Right? So time series plots are invaluable for the stock market, but also, like you said, for sales. Yep, for sales. You know, so they're useful for a lot of different things. Right? Here's an example where they build a time series plot for crime data here. Now this data set here represents the number of violent crimes committed per 100,000 citizens every 5 years from 1980 to 2020. Draw a time series graph for the data and use it to discuss trends in violent crime. So trend analysis is one of the most frequent things that time series of plots are used for. Because like I said, if you can model the data as to what's happening with it versus time with some sort of like an equation, you can model the trend by using an equation. You could use that to make predictions or forecasts about the future. And that's really what it's all about. And there's many sophisticated trend models that you can use to try to model data. A couple that come to my mind would be something called an auto-regressive integrated moving average, or an ARIMA model, ARIMA, auto-regressive integrated moving average model, ARIMA. Box-Jenkins techniques are also used to try to model trends within data, okay? And I had a chance many years ago when I taught a course in quantitative management, had a chance of building these models using a computer and a software program. So if you want to look into those, like I said, the first one was a ARIMA model. That stands for, again, auto-regressive integrated moving average model. These are popular models used to try to analyze trends with data, and then you can use that model to make predictions. So ARIMA models. The other one I mentioned was like a Box-Jenkins method. If any of you ever are interested in this, Jenkins is Jenkins. Just to name a few. I'm sure they have other models by now, because that was many years ago when I taught that course. But yeah, trend analysis is critical in making informative decisions out there that can mean the difference of losing or making millions and millions of dollars. Okay. All right, so here we have data from 1980 to 2020, violent crimes per 100,000 citizens. So this is like kind of like a crime density, if you will, where you're dividing the number of violent crimes per 100,000 citizens in a society. I like to think of it as being like a density of crimes here. And you can see that for these years, the highest density of violent crimes was 1990, where for every 100,000 citizens, 729.6 violent crimes occurred. So let's see if we can make a time series plot for this data here. And the horizontal axis will represent the year. Notice they have the years evenly spaced. The vertical axis represents the number of violent crimes per 100,000 citizens. You know, whenever you make any sort of graph, it's critical that you label the axes, because if you don't label what the axes represent, then the reader's not going to know what the graph even pertains to. So it's critical to always label your axes. In other words, if I did not label my vertical axis, would we even know what these numbers pertain to if I did not label my vertical axis? All I see are 0 to what, 800. Do you agree? We wouldn't have a clue as to what those numbers pertain to. Critical, labeling your axes. Oh, those are the number of violent crimes per 100,000 citizens. That's very important. Right? So what does it look like the trend is doing here with this data? Is the number of violent crime density increasing or decreasing versus time? In other words, is it on an upward trend or downward trend?
Upward.
Well, it was on an upward trend from about 1980 all the way up to what, 1990-ish. But then from that point onward, it looks like there's an overall what type of trend?
Downward.
Downwards in general. it looks like it drops pretty quickly between 1994, well, 95 to 2000, and then it starts leveling off a little bit. Okay, and even increasing a little bit from 2015 to 2020 there. So like I said, time series plots are invaluable for giving us a very quick snapshot as to the trends that exist within data. You can determine a lot more from a time series plot as opposed to sifting through raw, unsorted data points. That's a certainty. So graphs are a very powerful way of conveying information about data very quickly and in a very pleasing way, as opposed to sifting through reams and reams and reams of millions of unsorted data points. So pictures and graphs or tables are invaluable for organizing your data so that you can see what type of picture or meaning the data set's trying to convey to us. All right, so these are a couple of graphs, basic graphs that we are dealing with in this section 11.2. So let's see if we can go to our book now and maybe try a couple of these out here. All right, so we're going to be hanging out 11.2 today. This section is entitled Picturing Data. Okay. And I think I told you, indicated a couple of days ago that, you know, you've heard the phrase, how does that go? A picture is worth 1,000 words or something. Well, in statistics, ladies and gentlemen, a good graph is worth 1,000 data points. Okay. But that's true though. You can ascertain a lot of information very quickly about graphs compared to, you know, looking at raw data, especially when it's unordered. All right, here's a complicated bar graph. You ever see one of these before? Reading a complicated bar graph. As vaccines for COVID-19 became available in late 2020, the Kaiser Family Foundation began a monthly survey of adults about their intentions in regard to vaccines. The results were summarized in a bar graph. Note that some percentages don't add up to 100 due to undecided respondents. Describe the trends among those who have already been vaccinated, et cetera, et cetera. Well, can we even understand how to read this thing? Our vertical axis is time. Notice December 2020 all the way through June 2021. We have different categories represented by different colors here. What is that color? I don't know, light green. Already received the vaccine. The peach color is like as soon as possible. Yellowish color. Wait and see. Turquoise, only if required. Definitely not is the pink color there. So let me ask you this question here, Lizzo. Let me ask you this question. As time progresses, as we go on in time from December 2020, what's the overall trend in this data? What's kind of happening here? Can you kind of see a trend here? What's kind of like, what's the major change from 2020 to 2021?
Most people got the vaccine.
Yeah, basically, that's you know, the number of people that actually receive the vaccine actually increases. Okay, and therefore the other categories tend to become smaller. So that's the overall big trend that you know, the data is showing us. What I find interesting is what category is not changing. Interesting. It looks like there's two categories that are really not changing. What would it be?
Definitely not,
blue.
or only if required.
Yeah. It's the, the turquoise and the pink. These bars are about the same length. They're not changing. So we have, some people that are not budging right here, correct? Not budging at all. And it looks like in general, these people are not really budging with their opinion either. See that? Interesting. That's worthy to note. Looks like the other ones are changing though as time progresses. All right, so that's an interesting bar graph. That gives us a snapshot as to the comparison of different groups. That's a very useful plot there. Okay. All right. So let's see if we can go down and have some fun here. All right, so ladies and gentlemen, what I want you to do for classwork number 1 is problem number 9. Let's see if we can draw a bar graph for the number of transplants of various types performed in the United States in 2020. Then use your graph to analyze the data. We got kidney, these are all organ transplants, kidney, liver, pancreas, heart, and lung. I would like you to make a bar graph. Go ahead and do that. You could probably have your bars going vertical, or if you insist on having them go horizontal, there's nothing wrong with that. You can do that too. Oh, very important. Make sure you label your axes. Very, very important. Okay, go ahead and do that. We'll call that classwork number 1. Constructing a bar graph. All right, are we ready to look at this or not? Number 9. How to build a bar graph for the number of organ transplants performed in the US in 2020. Okay. The horizontal axis will probably be labeled to what? The type of transplant. Kidney, liver, pancreas, heart, lung. Vertical axis will be a numeric axis. And the scaling that you choose, ladies and gentlemen, you just got to make sure that, you know, you choose an appropriate scale on your vertical axis that will accommodate all the way up to about 22,817. So, I mean, your vertical axis cannot just run from like, you know, 0 to like 10,000. That's not good enough because you're going to be excluding the kidney category here. So you got to make sure your vertical axis, you know, runs the full gamut here. And how you space your tick marks is up to you. Obviously, we're probably not going to be able to space the tick marks from 0 or 1 unit apart from 0 all the way up to 20, like 3,000. That's not happening. Okay, so maybe you want to space your tick marks. I don't know. Did anybody have an interest, a good way of spacing vertical axis tick marks? Anybody? How many units apart did you space your vertical tick marks? Anybody? $100 units apart, 500 units apart, what? 1,000 units apart?
I did by 2000s.
By 2,000. Okay. Yeah, that seems reasonable. We do have kind of an awkward scale here in a way because we're going like, you know, obviously we got to start at 0, and that makes things tricky because we got to get all the way up to 22,817. Okay. So the key is, you know, just make sure whatever scaling you use that your tick marks are evenly spaced. That is very important. And just because you used a different scaling on your vertical axis as opposed to what I'm about to show you doesn't mean your graph is necessarily wrong. Okay. You know, because there's a lot of different scalings we could go on the vertical axis. All right. Still have an accurate graph. All right. This is the graph that the author came up with. Notice on the vertical axis, they started at 0, and you know what? They did use a spacing of 2,000. Nice job on that one. But yeah, it seems like a very appropriate scaling, spacing your tick marks by 2,000. Did anybody else have a different scaling that still worked? Okay. Anybody? Anything different than 2,000 units apart? Just curious. All right, well, maybe you did, maybe you didn't, but you can see just at a quick glance that kidneys were the most prevalent, you know, transplants. I mean, you can ascertain that within about 1 second just by looking at this graph. Boom. So these graphs are a very powerful, quick way of ascertaining what your data is showing us, as opposed to sifting through raw unsorted data. Okay. Pancreas was the least. Okay. Transplant procedure. Heart and lung about the same. Liver is up there a little bit, but yeah, kidneys are they're a big one there. They're a big one. Does anybody want to weigh in as to why maybe kidneys is such a large category compared to these other ones? Does anybody know something that I don't know? Maybe anybody in the medical field or whatever? Why are kidneys, you know,
Kidney failure is linked to like drinking and alcohol, which is pretty common.
all right?
Yeah,
So
that's the liver one is like
what's that?
That's probably why the liver one's a little higher too. The alcohol,
Mhm.
an alcohol problem.
Kidney also filters things like caffeine and whatnot from your blood too. In America and all sorts of other countries are super high, you know, coffee drinkers.
Yeah, you know, it kind of looks like the liver and the kidneys are almost in tune with one another. Do you agree as far as the heights of the bars are concerned? You know, there is a difference. There's quite a bit of difference, but still, it looks like they are kind of like in tune with one another a little bit. So yeah, it kind of sounds like maybe that would be maybe a plausible reason. Because maybe the liquids we consume in general in this country. Let's see here. Does anybody think that it might be because how shall I say this? Are kidneys donated more readily than like heart or lungs? Does anybody know anything about the difference in donation rates for those organs?
Well, I do know that
People have, like-
generally.
Go ahead.
But okay, well, not speaking from like any medical experience, but I do know that like that more people are a bit more forthcoming with those specifically because they know they can donate at least one and still be
Yeah.
fine afterward.
Have like a spare tire. Yeah, I mean, I wonder if that has something to do with it too. But you know, I don't know. Maybe it does. Maybe it doesn't. Be interesting to talk to like a health professional that actually does these transplants to get their take on it. But I don't know. I'm just wondering. And pancreas is really low, and why is that? I don't know. I mean, is it because
The type 1 diabetic, I could answer that.
what's
The-
that?
Yeah, so the pancreas has an extremely high rejection rate from the human body. It's almost impossible to find like a safe match, and even then you have to take like medicine for the rest of your eternal life kind of deal to make sure your body doesn't, get rid of that organ like it would with your diabetes in the first place.
Yeah.
Basically, your autoimmune system is constantly attacking the pancreas and the cells it produces, regardless of if it's a transplant or not.
All right, great. Yeah, I didn't know that.
Yeah.
So pancreas is very difficult to transplant and have it be accepted by the body, correct? It just doesn't not really readily acceptable as the other ones are. The kidney, liver, maybe the heart, lung, and stuff like that. So that's just interesting. Just to throw some ideas around as to why maybe these frequencies are the way they are here. Okay. Hey, I pulled up a problem on Alex regarding a circle graph, and I want to kind of walk through this problem, and it'll show you how to do a future problem on Alex. It says in a survey of 100 college students, the numbers shown here indicate the primary reason why the students selected their majors. Draw a pie chart for the data. Of 100 people, so students surveyed, 60 said that it was out of interest that they selected their major. And that's good to see, because I always tell students, always start with your interest as far as what career you want to lean towards. That's critical. I mean, if you're not interested in something, then your job's going to be drudgery every day. That'd be awful. So always start with your interest and see if you can turn it into a career. Future earning potential was a fairly big one, but interest is the biggest. Pressure from parents, and good job prospects. Okay. Anyways, we're going to try to build a circle graph from this data table here. And of course, these numbers should add up to what? 100. Do you agree? Hey, if they did not add up to 100, should we even be building a circle graph, do you think? If they added up to like 200? In other words, if a college student could basically answer or check off more than one of these reasons, would you want to use such a data table to build a circle graph in that situation? The answer is probably what? Probably what not. Do you agree? In such a situation, in that case, you'd probably want to build a bar graph instead. So we're assuming that each of these 100 students that were surveyed, they could only answer one or check off one of these reasons, only one. That's the key to building a circle graph. There cannot be multiple answers, okay? If that's the case, you really should be using a bar graph. The circle graph just won't work. All right, anyways, these do that, they do add up to 100, and here's how your author's having us deal with this. Instead of dealing with it in terms of degrees, ladies and gentlemen, they have us dealing with it in terms of percents. Notice this circle starts at 0% up on the top, and as we rotate clockwise, the percent increases by 5. So each tick marks represents 5%. So 0%, 5%, 10%, 15%, 20%, 25%. 30, 35, 40, 45, 50, 55, 60, 65, 70, 75%, 80, 85, 90, 95%, and 100%. That's a cool way. All right, so here's what we got to do. We have to divide each of these frequencies by the grand total number of observations. And so 60 divided by 100 would be what percent? And how nice is that is that these add up to 100, because percent means what? Per 100. Do you agree? So turning these into percents is going to be trivial. 60 over 100 is what percent? That's called 60%. Do you agree? Now, how do I answer this question? I would type in 60 here. Now, the next category is future earning potential, and that was what? A 17%, 17 out of 100. All right. Wait a minute here. What just happened there? Well, all right, pressure from parents would be 14%. And good job prospects is 9%. Let's see, is this going to work or? But it's that simple, and it should make this graph, I think, automatic. Does it make it automatically or? Yeah, I don't know what I did. Anyways, ladies and gentlemen, you can kind of see it here. It looks like it's working. 60% obviously is the largest sector of the circle, which represents the the category interest in the subject was the motivation for choosing a major. And of course, good job prospects is, up there. I find it interesting that that wouldn't be larger, good job prospects. I mean, you want to be able to get a job in it, but I don't know. I find that kind of interesting. It's a little like that. Pressure from parents, it's in there. And future earning potential is right up there. But that would be your circle graph. It's based on percents there. So, how would you do this manually? If you had this circle sitting on a piece of paper here, here's what you do. You'd start at 0% and you would rotate to 60%. Okay, so you go all the way down here to 60%. That leaves off the first category. Then you pick up with the future earning potential, and then you rotate 17 degrees from there, 5, 10, 15, and about 17 right there. And then you pick up where you left off with that purple sector, and you rotate 14 more percent. So let's see here. Year to year would be about 5%, about 10%. And let's see, about 14% would put the end of the purple sector right about there. And then you rotate 9% more, about 9%. So you just have to try to guesstimate as best as possible. And you'd have your circle graph there, right? So we check our answer. And it looks like we got it correct there. See? So that's how you're going to build a circle graph, ladies. It looks pretty simple, doesn't it? I mean, it doesn't look that difficult. Now, my only concern with this is, like for this purple sector, because where it leaves off and transitions to the pink sector, because it's not actually striking the actual tick mark value, we can only hope that Alex allows a little bit of latitude here. Do you agree? As to where you end the purple sector here. Because our tick marks, we're only at the mercy of our tick marks being spaced by 5%. All right. We're going to have to just guesstimate as best as possible where to leave off a sector. And let me know if, Alex, calls you on the carpet with that or marks it wrong. And, I'll take a look at it. If, as long as it looks like it's very close to where it should be, I'll give you the credit for it. But I would imagine Alex is pretty lenient and gracious in this department with respect to that issue. But again, let me know if it gives you any problem, okay? So, ladies and gentlemen, do you agree you could probably draw this circle on your paper? And you can label the 0%, 25%, 50, 75%. And in between each of those, you can put what? 5 tick marks, each representing 5%. So you could partition a circle up like this on a piece of paper, and you could probably build your own circle graph then, correct? I don't think that would be too difficult to do. All right, any questions about how we did this on Alex? It's really simple. It looks pretty easy. So based on what I've shown you there, see if you can maybe do, let's see, your pie graph for number 15. In fact, would you believe it deals with the same situation here, only the numbers are a little different here? So see if you can build a pie graph or a circle graph or a pie chart for number 15. And again, on your paper, just draw a circle to the best of your ability. And just label this as 0%, 25%, 50%, 75%. And just lay some tick marks off here, evenly spaced. There's 5%. There's 10%, 15%, 20%. You know, try to evenly space them as best as possible and go from there. Okay, go ahead and do that. We'll take a look and we'll see if you got approximately the correct answer. Okay, let's take a look at your circle graph here. Does it look like that? Does it look like about that?
Yeah, mine's a little backwards, but
All right.
it's the same.
It doesn't matter, like, like how you decide to label your, your slices of your pie or whatever, the pieces of your pie. The important thing is that they have they have the same size as this one. Is that correct? About all your categories have the same size sectors that are illustrated in this circle graph. If that's the case, your graph is just as good as anybody else's. In other words, what I'm saying is you could have maybe had, the largest slice, maybe the smallest slice for like good job prospects. Maybe it was like up here. Maybe that was your good job prospect piece there. Okay. So it doesn't really matter what order you have these labeled. The key is that each category has the same size. That is the important thing. About the same size as what you're seeing here. If it does, yours is just as accurate as anybody else's. Okay. All right. Now let's go on down here to see if I can have you build a frequency histogram from this data set here, number 31. 30 American sedans and trucks were tested by the EPA for fuel efficiency in miles per gallon. The frequency distribution shown here was obtained. Draw a histogram and frequency polygon for the data. So ladies and gentlemen, not only do they want you to draw a frequency histogram, they want you to draw a frequency polygon. So we're going to have to add an extra column on here. And what other column are we going to need for a frequency polygon? We're going to need the what column? The midpoint? We're going to need the midpoint of each class. So how would you find the midpoint of like the first class 8 to 12? You would say 8 plus 12 divided by what?
2.
Yep, so that'd be 10. So your midpoint for the first class will be 10. And you got to find the midpoints for all the other classes before you build your frequency polygon graph. Okay, go ahead. Build a frequency histogram and a frequency polygon for this frequency distribution table here. Have the Lucas in their conference. All right, ladies and gentlemen, this is what your frequency histogram should look like. Horizontal axis, miles per gallon. Notice they did not even label like the lower end point of the class. Like they didn't, like notice this, they didn't actually put like an 8 here. They didn't put like an 8 here. And then they didn't run it all the way to 13 here. You see that there? See, they're not doing it that way here. Okay, and then they didn't take this to 18. Okay. Another way to label your classes is to use this method they're showing you here. Just like 8, this first bar represents the class 8 to 12, second bar 13 to 17. That's okay. There's nothing wrong with this way, this convention. Did anybody go from like 8 to 13 to 18 to 23 to 28? Anybody do that? And then it would be what, 33? Anybody do this convention here? Label the classes that way? That would be okay also. So either this way or the way they have it here. Either way. Bottom line, what's the most frequent miles per gallon fuel economy? Between 18 and what, 23 miles per gallon? Do you agree? You can discern that really quickly. Notice this distribution is very symmetric. We have a symmetric, we say bell-shaped distribution, ladies and gentlemen. We would say these fuel economies are normally distributed in statistics, normally distributed. And we'll have a chance to touch base with this very important normal probability distribution that looks like a bell-shaped curve like I just drew here a little later on in this course. Okay. All right, that's what your histogram should look like. What about the frequency polygon graph? This is what it should kind of like look like. Notice the horizontal axis is still miles per gallon. The vertical axis is still the frequency axis. But now they use the midpoints of each class to connect these little line segments. So this is the midpoint of the first class, which is 10. This is the midpoint of the second class, which is, I think, 15. Midpoint of the third class up here. Next class midpoint, next class midpoint. And that would be your frequency polygon graph here. Notice they start at 0 down here. They evenly space these tick marks by 5 units, and they start at 0, and then they go all the way up to the first midpoint of the first class. And notice they take the last midpoint of the last class all the way down to 0, 2 to the next tick mark. Notice that interesting feature there. But that makes sense there. Okay, that's how you do a frequency histogram and a frequency polygon there. Okay. All right. Okay. Now, time series plot here. We don't have a lot of time left, but number 35, I want you to draw a time series graph for this small data set here. Following data represents the number of downloads per month of an iPhone app. Draw a time series graph for the data and use it to describe trends in the data. So go ahead, ladies and gentlemen, see if you can make a time series graph for this data set. Number 35. We have just enough time to maybe get this one last one in here. All right, so just a simple time series plot. Your horizontal axis might be like the month, and the vertical axis would be the number of downloads. And it's always worthwhile to note the range of your data, your numeric data, so you can establish appropriate scaling on the vertical axis. Our data ranges from about 12,000 to about 19,000, so you want to make sure that you have an appropriate scale so as to see this plot. Let's see what the author did there, and there you go. The months are on the horizontal axis and the number of downloads in thousands. Now it's important to, in parentheses, say in thousands. If you don't say in thousands, hold on a second, what just happened here? What's just going on here? If you don't say in thousands, ladies and gentlemen, what's going to happen is it's going to look like the person reading your graph is like, they're going to say like in May, there was only 13 downloads. No, there were about 13,000 downloads. Okay, so it's very important to qualify that. And there you go. You can see that there's an overall upward trend all the way from May to August, and then there's a slight downward trend from that point onward. That's called a time series plot. All right, and you could also almost model this according to like a linear equation. If you did linear regression on this, you could maybe model it according to a linear equation like this. Or you know what? You can maybe even model it according to maybe like a quadratic relationship that has a parabolic graph. That's a possibility too. Like I said, trend analysts in the stock market area and are always trying to model the data according to some sort of an equation, so they can use that equation to make some sort of prediction as to what's going to happen in the future. Okay. All right, I'll stay on the line for the next couple of minutes if you have any questions or comments. Otherwise, have a great weekend, and hopefully we'll see you next week as we are nearing the end of the semester very quickly. Ladies and gentlemen, just try not to get behind, try to finish this course so we don't have to take it ever again. Okay. All right, you have a good day.